Hello everyone, my name is Nadia Mesha and I'm here to present a paper written by Andrei Zaidel titled High Power FET Application in S-band Amplifier. Now the abstract for this paper is a 50-watt pulse amplifier design in S-band using Fujitsu gallium arsenide FETs is presented. The essential elements, namely FET characterization for power and efficiency, stability, and forward gate current protection are described. The paper concludes with some experimental results of the realized amplifier. When one designs an amplifier, they can choose either a set of necessary active elements or an amplifier's configuration. Now, a very useful method is to consider a balance of power and gain, which will ultimately determine how many stages will be indispensable and what kind of stages have there to be. To achieve requirements, bias conditions, stability, input and output matching, load impedance, and gain must be considered majorly. The first stage of the amplifier consists of an input and output matching circuit and a general-purpose gallium arsenide FET type FSX027WF. The next stage is built on a type FLM3 135-4F, and the last stage is built on a type FLM3 135-18F. Both are internally matched power transistors. Isolators are used to protect transistors against accidental damages, for example, in case when the output is left open. Each stage was designed separately and have been connected in a cascade by 50-ohm transmission lines. Now, this project used a CAD program called GENESYS because the input amplifier stages work with signal levels in the range in which operating characteristics are not dependent on signal voltage or current. It is possible to use small signal S parameters of FSX027WF to design the first stage. Next, the linear relations become unsatisfactory as the signal level increases, and we have a situation known as large signal operation. Each stage of a multi-stage amplifier must be individually examined for stability, as it is impossible to do otherwise. Instability can be the reason for damage by self-oscillation. In this case, FSX027WF is not unconditionally stable. Using GENESYS, we can analyze source and load stability circles on the Smith chart, which the results are shown in Figure 2 here. And the shader regions on the top bits of the Smith chart represent region instability. To ensure stability, the impedance is presented to the device at its input, and output terminals should avoid the shaded regions of the stability circles. This stability data are used to add stabilizing components such as shunt input, output resistors, and inductors to select an input and output matching network topology, which will properly terminate the active device at low and high frequencies in order to gain stability. The FET can be stabilized by inserting the resistance either in the gate or drain, and the next stages will become unconditionally stable. When using power gallium arsenide FETs, it is crucial to take into account the necessity of limiting forward gate current when the device is operating under high RF levels. Because under large signal drive conditions, the shorty barrier gate diode of the gallium arsenide FET will be driven into a forward condition. Now, if the associated current levels are too high, the accompanying thermal effect will gradually alloy the gate junction and degrade the action of the transistor. To limit gate diode current, it is common to use a series resistor in the gate bias circuit, but the resistor value must be chosen carefully, because when the resistance is too large, the amplifier power added efficiency will be diminished by limiting RF voltage excursion. On the other hand, too small a value will lead to long-term degradation of the transistor. Now we move on to the experimental results. Here we can see that the structure of the amplifier has been designed and optimized using GENESYS. A prototype of the amplifier has been realized on RT gyroid substrate and placed on a metal housing. Some properties that include output power level and gain versus frequency and saturation characteristics have been measured. You can see in figures 3 to 5 present. Now to summarize this paper, an S-band power amplifier has been presented and some important aspects of the designing procedure have been discussed. Theoretical predictions and measured results correspond quite well with one another. The main goal, which is to produce an output power in between the band range of 3 to 3.5 GHz, has been reached. Thank you for your attention and have a good day.